In this video, we discuss learning outcome number 3 in lesson 5.2, which is all about applying 4 methods for computing binomial probabilities. So we'll summarize those 4 methods here. The first method is the intuitive approach. This relies on the multiplication rule and the addition rule that we've already studied. Now, among the methods listed on this slide, this is the least efficient approach, and most students aren't going to use it. But studying the intuitive approach is important because it helps you understand why the formula that we're going to talk about in our second method is true and useful and where it comes from. And it also helps us to understand the values that we see in a table of binomial probabilities or the values that we see in the output from technology. So we can use the intuitive approach, and that's going to help us understand what's going on. We can use a formula. I use a formula a lot as I'm working through homework problems on the homework help playlist. You can use technology. I'm going to show you how to use Excel. And lastly, you can use a table of probabilities. So first of all, I'm going to skip that intuitive approach until we look at an example. Let's look at that binomial probability formula. So here it is. Looks a little daunting. Looks like alphabet soup. But remember, n is the number of trials, x is the number of successes among n trials, p is the probability of success in any one trial, and q is the probability of failure in any one trial. So what this says up here is that the probability of x successes in n trials is given by this formula. Now, all of the pieces of this formula come from using that multiplication rule and the addition rule, as we'll see when we look at the intuitive approach. Now, the x values over here range between 0 and n inclusive. X is one of those whole numbers because x is the number of successes in n trials. So if you have n trials, you could have 0 successes, you could have 1 success, you could have 2 successes, you could have as many as n successes. Maybe all of your trials are successful, and that's great. But you can't have n plus 1 successes if you only have n trials. And of course, you can't have a negative number of successes. That doesn't make any sense. So that's why x has to take on all of these values. Now let's apply both the intuitive approach and that binomial probability formula in an example. Here's our problem statement. It says, standardized tests such as the SAT, ACT, and MCAT typically use multiple choice questions, each with 5 possible answers, A, B, C, D, and E, one of which is correct. Assume that you guess on the first 4 questions. Find the probability of getting exactly 2 out of 4 correct. And then here I'm just summarizing what I just said. Oh, I see a typo. I think I'm going to fix it right now as I'm making the video. Sorry, guys. There we go. So we've got multiple choice questions. There are 5 options. Only 1 is correct. You're guessing on 4 questions, and we want the probability of getting exactly 2 out of 4 correct. Okay, so here's our solution. Before we use the formula, I want to show you the intuitive approach. We're going to use the multiplication counting rule and the addition rule to find the answer. And then we're going to show that the formula for binomial probabilities gives us exactly the same result. So let's start here. Suppose you've got 4 problems. You're guessing on these 4 problems. And you guess the correct answer on the first 2 problems, and you guess incorrectly on the last 2 problems. If you want to find that probability, the probability of 2 correct answers, followed by 2 wrong answers, according to the multiplication counting rule, all you do is find the probability, or I guess it's not the multiplication counting rule, it's just the multiplication rule. You find the probability that that first answer is correct, and you multiply by the probability that the second answer is correct, and then you multiply by the probability that the next answer is wrong, and then you multiply by the probability that the last answer is wrong. So what you get is 1/5 times 1/5, because you have a 1 in 5 chance of being correct if you've got 5 answers and only 1 of them is correct and you're guessing. And then you've got a 4 in 5 chance of being wrong. If you multiply all of those together, you're going to get 16 out of 625. Now, that's not going to answer the question. The question says, what's the probability of getting 2 correct and 2 wrong? It doesn't really matter to us if the first two are correct and the last two are wrong, or if the last two are correct and the first two are wrong. The arrangement of those two correct answers and those two wrong answers really doesn't matter. We're just interested in the probability that 2 out of the 4 are correct and the other 2 are wrong. So in order to find the probability that 2 of them were guessed correctly and then 2 of the answers were guessed incorrectly, we have to think about all the possible ways that we could choose to get 2 correct answers out of 4 questions. So here are the possibilities. Let's say the first answer is correct. Well, if you've got 2 correct answers, the first answer could be correct and the second answer could be correct, or the first answer could be correct and the third answer could be correct, or the first answer could be correct and the last answer could be correct. Now let's say the first answer is wrong and the second answer is correct. Well, there are 2 ways that that could happen. You could have the second answer that's correct and a third answer that's correct, or the second answer that's correct and the fourth answer that's correct. Or it might be the case that both the first and second questions are incorrect. Then the only way that you could have 2 more correct answers is if the last 2 were correct. So if we're going to have 2 correct answers out of 4 guesses and 2 incorrect answers there are actually 6 ways that that can happen, and they're shown right here. Now, so that means we've got 6 arrangements where we've got 2 correct answers and 2 incorrect answers. And it turns out that all of these have the same probability. So for the first one, we said that the probability of getting the first 2 correct and the last 2 incorrect was 1 in 5 times 1 in 5 times 4 in 5 times 4 in 5. Or 1 in 5 squared because you had 2 answers correct, and 4 out of 5 squared, multiplying those together because 2 of the answers were incorrect. So that's the probability for this first one. For the second one, the probability of getting the first one correct and the third one correct and the other 2 incorrect is 1/5 times 4/5 times 1/5 times 4/5. The probability of this happening right here is 1/5 for that first correct answer, 4/5 times 4/5 for those 2 incorrect answers in the middle, and that last answer being guessed correctly would have a 1 in 5 chance. And notice that every single one of these has 2 correct and 2 incorrect. So whenever you calculate that product, you're going to have a 1/5 and a 1/5 multiplied by a 4/5 and a 4/5. And because multiplication is commutative, you can multiply in any order you want. So the probability of each of these events is exactly the same. It's the same probability as when we calculated the probability of getting the first 2 correct and the last 2 incorrect, or the last 2 wrong. So each of these has a probability of 16 in 625. So now if I want the probability that 2 out of 4 are correct, I need to add the probability that this happens to the probability that this happens to the probability that this happens, and so on for all 6 of those arrangements. Since they all have the same probability, I can just take this probability right here and multiply it by 6. And I get 96 out of 625, which is 0.1536. So this is saying if you have 4 questions and you want to know what is the probability that 2 of those would be guessed correctly and 2 would be guessed incorrectly if you're guessing the whole time, you have a 15.36% chance of getting 2 out of 4 correct just by guessing. Now, I wanted to show you that this gives you exactly the same result as this binomial probability formula. This expression over here on the right-hand side, this is the result that we get from that multiplication rule. Remember, P is the probability of success in one trial, and X is the number of successful trials. So if I have a probability of success of 1/5, and I'm successful X times, I'm going to have 1/5 times 1/5 times 1/5, a number of times. How many times? X times. Now, for the remaining positions, Well, if we succeeded X times, we failed N minus X times. The probability of failure in a single trial is Q. So by the multiplication rule, we would multiply by the probability of failure, by the probability of failure, and by the probability of failure again, N minus X times. So we would have N minus X of those multiplying each other, and so we could just write this as an exponent. This is the same as that 1/5 squared, because that was a probability of success squared. We had 2 that were correct, times that 4/5 squared, because we had 4/5 as the probability of failure in one trial and 2 were incorrect. Now, if I'm just looking at this, this is the probability of getting the first X correct and the last N minus X, the remaining questions incorrect. So that's just the probability for one of those arrangements. But we don't want just one of the arrangements. We want all possible arrangements that lead to that result. We want all 6 of these guys. In order to get all 6 of those guys, we've got to multiply by this factor right here. That factor, I hope you recognize it, that is combinations. That is the number of ways that we can choose X positions out of those N positions to put our correct answer in. That is the number of outcomes that have exactly X successes among N trials when we don't care about order, when we're calling all of these guys exactly the same. So that's why I use that formula for combination right there. So if you multiply this 6 by the probability of getting 2 correct and 2 incorrect, then you get the probability of having exactly 2 successes among 4 trials. But this extends for N trials and X successes as well. So now hopefully you know and you understand where this formula comes from. This piece has to do with the arrangements, all of those possible ways that we could choose X out of N positions to be successes. And then this is the probability over here, this factor on the right is the probability of having X successes in the first X positions and then N minus X failures in those last N minus X positions. Now, I wanted to show you that if you use the binomial probability formula, you're going to get exactly the same result. So there's our formula. Here we're talking about guessing on 4 problems. And we want to know what's the probability of getting exactly 2 of those correct. So X is equal to 2. Using this formula, we've got N factorial over 4 minus 2 factorial. That's N minus X factorial times X factorial. That's the number of ways that you can choose 2 of those problems to be correct. And then you multiply by the probability that the first 2 are correct and the last 2 are incorrect. So you got that 1/5 times 1/5, which is 1/5 squared. It's the probability of success raised to the number of successes, because that's how many of those factors you're going to see in the multiplication rule. And then you've got the probability of failure here raised to the number of failures, because that's how many of those factors you would see due to the multiplication rule. Now, this 6 out front comes from the addition rule, because you're adding all of those probabilities from the different arrangements together. Now, if we simplify this, 4 factorial over 2 factorial is 4 times 3. So that 2 factorial is gone. Now, this 2 factorial is this 2 times 1. So 4 times 3 is 12. 12 divided by 2 is 6. That's those 6 arrangements that I promised you. That's those 6 arrangements right there. So we've got 6 times 1/5 squared times 4/5 squared, and that gives you 96 over 625, which is 0.1536. So we get exactly the same answer using the formula. So you can trust this formula. I use this formula a lot when I'm going through homework problems with you guys, because you'll have access to this formula. You'll also have access to a table of binomial probabilities during your exam. Okay, so the first method was intuition. And that's the least efficient method of all the methods that we're going to talk about. The next one was the formula, but the formula itself agrees with intuition. So now you can trust it because you know where it comes from. Now you can just apply it if you want to. Now, even more efficient than using that formula is using technology. So technology can be used to find binomial probabilities. I'll show you some screen displays on the next slide. They're going to list binomial probabilities for n equals 5 trials and a probability of success of 0.85 in a single trial. I want you to notice as you look at that slide that the probability distribution is given as a table. I'm going to teach you how to make that kind of table in Excel. So notice that we said that n was equal to 5 and the probability of success in one trial was 0.85. And we're looking at this TI-8384 plus display. In that first list, you have the number of successes. So if there are 5 trials, you could have 0 successes, 1 success, 2 successes, 3 successes, 4 successes, or 5 successes. And then each of those is associated with a corresponding probability. That's what the second list shows you. So according to this, the probability of getting X successes, or excuse me, 3 successes out of those 5 trials is 0.13818. And notice that you get the same output with a program called Minitab, and you get exactly the same output in Excel. I'm going to show you how to do that in a minute. And then StatDisk will also give you similar output. Now, when it comes to using technology, I know that many students have a TI-83 or 84 plus. You are welcome to use those on the exam. I'm not going to show you how to use them. Instead, I'm going to show you how to use Excel. And the reason I show you how to use Excel is that most students, after they leave TCC and while they're at TCC, are going to have access to Microsoft Office products. You're going to be using Microsoft Word at work. You're going to be using Excel at work. You probably have a version of it for your home. If you don't have Microsoft Office, you can get a version of it from TCC because you're a student. But everyone uses Microsoft Office, or almost everyone uses Microsoft Office in the workplace. So I wanted you to be familiar with how to do all of this in Excel. And it's actually really easy. Now, you won't have access to Excel on your exam, but if you're using if you have large data sets, or maybe you're looking at a large number of trials. So maybe n is equal to 28 or n is equal to 40, like you're going to see in this next example. It makes much more sense to use something like Excel to get those answers for you. And I'm going to show you it's very, very easy. So here is the function that we use in Excel to get binomial probability distributions. This is actually a screenshot of a website. It's from dummies.com. They're the same people that published the For Dummies books, so like Statistics for Dummies. It shows you how to use this binomial distribution formula, this function in Excel. So if you click here, you can read about how to use it in the For Dummies website. You can also click here. It's going to take you to the same place. And we're going to use this function in just a moment when we do the next example. So here is the next example. So suppose your upcoming statistics exam includes 40 multiple choice questions with 4 options each, A, B, C, and D, only one of which is correct. Suppose you did not study and you guessed on 40 of them. You guessed on them all. The question says, what's the probability of getting at least 28 of those questions correct? Now, 28 out of 40 corresponds to a grade of 70%, so that's a C. And this says, what's the probability of getting at least 28 questions correct? So we want X to be equal to 28 or greater than 28 because you're hoping to get 28 correct or 29 correct or 30 correct. Any of those grades would be fine because those correspond to an A, B, or C on the exam. And I think most people want at least a C in the class, if not a B. Or if you're really ambitious, you probably want that A. So let's see what the probability of getting 28 correct is if you didn't study and you guessed on all 40 questions. Now you can imagine that you don't want to do this by hand using the formula. So technology is absolutely appropriate here. So we want this probability that X is greater than or equal to 28 so that we can get an A, B, or C. In order to do this, we need to find n, that is the number of trials, x, the number of successes that we're hoping for, p, that's the probability of success in a single trial, and q, that's the probability of failure in a single trial. So we've got 40 questions, n is equal to 40. Now the number of successes that we're looking for, well, it actually takes on a range of values. We want x to equal 28 or 29 or 30. Any number between 28 and 40 would be great, because then you're getting an A, B, or C on this exam. Now, if you've got 4 options for a question and only one of them is correct, you've got a 1 in 4 chance of guessing correctly. That's a probability of success of 0.25. If you have a probability of success of 0.25, your probability of guessing incorrectly is 0.75. And again, if you want x to be greater than or equal to 28, so you want to guess correctly on 28 or more problems on this exam, what you want is the probability of getting 28 right or 29 right or 30 right. And then remember, we use that rule for the probability of A or B. That's the addition rule. So you have to find the probability of all of those, and then you'd add those together. Now that's a lot of calculations. That's 12 different calculations using that formula. Let's not do that by hand. Let's use computers. That's one of the things that our computers are so good for. Okay, before we look at this slide, let me show you how to do this in Excel. Oops, I've already done it here. Let me start with a new sheet. Okay, first I want x in this column, and you can have between 0 and 40 successes if you are guessing on 40 problems. So I'll just type 0 there, and here I'll type equals, and I want that 0 plus 1. If you drag and drop, oh, we only want to go to 40. Those are all the possible numbers of successes. So you could have between 0 and 40 successes in 40 trials. Now over here, if I want the probability of getting x successes, I will type in this cell. Let's zoom in a little bit more. And this is one of the things that's so wonderful about Excel. You type equals, and then you start to type that function, binom for binomial. And you see that binomial distribution on the list. Click that one. You see that fine print there? It tells you what they want. Oops, I don't think it's letting me zoom in right now because I'm already in a function. But the first variable that you need to type in is the number of successes. So I'm going to say I want the binomial distribution with x successes. And after this, they want the number of trials, 40 trials. And they say, what's the probability of success in one trial? 0.25. And then this last one is asking you if you want a cumulative probability or a probability of exactly x successes. So with cumulative probabilities, you'd be looking at the probability of x successes or less successes than that. So you'd be adding up all of the probabilities on this list for that x value and all the probabilities before it. That's not what we want here, so I'm just going to say false. I don't want a cumulative distribution, I just want the probability distribution for a binomial distribution. Hit enter. And then just drag and drop. Isn't that nice? Now you have probabilities for 0 successes through 40 successes, and all you had to do was type in that function and then enter the right input values. Okay, now the question said to find the probability of getting 28 problems right or more than 28 problems right. So we're going to add up the probability of getting between 40 and 28 problems right. So everything starting here at x equals 28 through x equals 40, close parentheses, and then we get that value right there. Looks like I'm getting a different number this time than I got last time. Let me make sure I'm doing this correctly. So that's got a 2 in it. That's got a 7. Yep, this is right. I think my slides are just wrong. I think I may have used the wrong probability of success in one trial. I may have been thinking of 1 and 5 being correct, or the probability of success, but we actually had 4 options on this problem. So the probability of getting 28 problems right, or 29 problems, or 30 problems, all the way through 40 problems is actually very small if you're guessing on all 40 problems. It's approximately 2.84 times 10 to the negative 9th. Let's go back to our slides. Okay, and actually that's wrong because I must have typed something in wrong before. So it's 2.84 times 10 to the negative 9th. So I have 2.84, and I've got 8 zeros in front of it. 8 zeros in front of that too. Okay, that's better. That's the correct answer now. So the probability of getting 28 or more problems correct is 0.000 or 0.00000000284. So obviously, it's very unlikely that if you guessed on all 40 problems that you would get an A, B, or C. So you definitely don't want to do that. Now you can still get an A, B, or C. You just can't guess on all of them. You've got to study, you've got to work hard, you've got to ask questions when you don't understand something. And then your probability will be much higher, much, much higher than what you would get due to chance, just random guessing on multiple choice questions. Okay, so we had 3 methods so far. You can use the intuitive approach, which no one really uses, but I wanted you to see where that formula comes from. Then you can use the formula, which I tend to do a lot in the homework. It's not too bad, but it can be tedious. Like I definitely wouldn't want to use the formula on this one. I'd have to use the formula 12 times for each of these probabilities. And I'd be here for a really long time if I was doing that. And then I'd have to add them all together. So using technology, that's a great method. That was our 3rd method.